Hello, I welcome you all. In this particular video, we're going to be solving the second problem. We already solved this one in the first video. You can check it out. We are solving this one. And in this particular problem, we have been asked to determine the angle theta less than or equal to 45 degrees at which the ball starts to leave the surface of the cylinder. Okay. Right, both problems are coming from the Engineering Mechanics and Dynamics, our 14th edition by RC Benam. So let's talk about what we are trying to solve here. So we do have three conditions for the normal force. When the normal force is greater than 0, this simply means the ball is in contact with the surface. Okay, when the normal force is equal to 0, it means the ball is at the verge of losing contact with the surface. Here we are talking about this ball here. Okay, and then finally we do have when n is less than 0, it means the ball has lost contact with the surface. All right, and the question here is to determine the angle at which the ball starts to leave the surface. So it is at the verge. So we are dealing with condition number 2. Okay, so we are dealing with this condition. Therefore, we want to find the equations that governs the angle at which the ball starts to leave the surface. So let's draw the free body diagram. Of course, we are dealing with the polar coordinates, and these are the ones I'm indicating right now. This is our r radio and this is theta. Okay, we have theta, we have r, and then we have the weight. Okay, and then we do have, let's indicate the normal force. I still need to indicate it even when we know that we have this. We are supposed to find the equation. So maybe this one is tangent to that particular point. We are trying to draw a tangent line. All right, something like so. So we expect our normal force maybe to be something like that, right? And then we also do have a force at this point from this particular arm, like so. Okay, so these are the components of our forces. Then we do have this angle here, which is negative clockwise. So this is our force exerted on the ball by this particular arm, OA. We have W, and then we do have the normal force N. But mind you, we've said our normal force is equal to what? This normal force is equal to 0. All right, so there'll be no need of even indicating the components. All right. So in this particular instance, let's identify the angles that we have. So this angle here is theta, and if this is theta, we expect this angle here to be 90 minus theta. Okay, is that fine? Yes. 90 minus theta, right? And if that is the case, then this angle here, so this is 90 minus theta, therefore this one here is theta also, right? Right, this is theta. Great. So having said that, let's work out this particular problem. And then let's say we do have our acceleration in that direction like so. These are the kinetic diagram showing the motion. This is our a arrow and this is our a theta. Okay, this is our a arrow like so. Then what do we have now? Let's write down the equations. But before we do so, the weight will have some components. The weight will have some component. One component will be along this direction. Okay. And then the other one will be along this direction. Right? So this one is just W cos theta. And then this one is W sine theta. Is that so? Yep. I think this is about it. W cos theta, and then this one is yes. So then there is no need of finding psi, we can just go directly since our n is equal to 0. So we have our r, which is equal to 2 rc, where rc is a constant. This is important, and if it's a constant, when we take derivatives, this is a constant. Okay, so r dot, which is derivative of r with respect to time, this just becomes minus rc theta dot, then sine theta. Then r double dot, this is just going to be equal to, we factor out this, and then we use the product rule. We find the derivative of one while holding the other one constant, and then we do the same for the other one. Then we'll have something like so. Okay, great. And then what else? We have theta naught, and it is constant, and therefore if this is constant, then we expect theta double dot to be equal to 0. Okay, all right. So then let's apply the equations of motion. Which direction do we go? So we have r, and we have r, we have this component and that other one, and then we have w, we have the other direction. All right, we'll do both of them. Let's see what we have. The idea is to just write theta itself. So summation of forces in the r, this is just equal to MAR. What do we have in that direction? We have a minus W sine theta, right? What else? and this is just going to be equal to MAR. Okay, and our AR is just equal to R double dot minus R theta dot squared, and this is equal to minus 2RC theta dot. This part here is 0. Okay, so we can exclude it there. So this just becomes theta dot squared cos theta. Okay, and minus R theta dot, right? And these theta dots, will include just the nodes like so. Okay, yep. So we can write this as minus 2RC theta dot squared, then cos theta minus R, and what is our R? Our R, let's write this there. So our R is equal to 2RC cos theta, and then theta naught squared. This is our R. Therefore AR is just going to be equal to minus right 2RC theta naught squared like so, and then cos theta these are two of them, right? 2RC theta, okay, cos theta, 2RC cos theta with this. Okay, so this is just a 4 here, so it's by 2, so this is just a 4 like so. All right, okay, let me come the other side. Okay, there we go. All right, so we have minus W, which is just our mg, minus mg mg sine theta, and this is equal to minus this is equal to minus m. We do have m there, so we can say minus 4 RC theta dot squared, then m cos theta. Okay, so this can cancel each other, and then divided by m there, then our theta, then this, once we divide this, then we'll have a tan theta is just going to be equal to, so we divide both sides by, this is coming from, let me show it so that somebody does not get confused somewhere. So we divide this by cos theta. Okay, so this just becomes 4R C theta dot squared naught divided by G. Therefore, our theta is just going to be equal to tan inverse of 4r c theta dot naught squared divided by the acceleration due to gravity. I think this is about it. This is really about it. We have found the value of, the expression that governs theta, okay, at which the ball starts to leave the surface. Okay, so I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and I'll see you in my next screen.